We are going to finish up focus 8. So we're going to talk a bit more about atoms before we move into molecules. So we're on 8C, and we're going to talk about periodic trends. There isn't a lot of new information, a lot of new understanding since Gen Chem in this section, because a lot of these things are very abstract, and it would take a much deeper understanding of quantum mechanics to put more information or actually derive some of these properties. So this should look similar to Chem 107, at least C, and then D will be slightly different. So we're going to talk about atomic and ionic radius, ionization energy, and electron affinity. Those are the periodic trends. And I wanted to make a correction. I hate it when I'm doing these recorded lectures and I hear myself saying something wrong, but sometimes you get tired and you don't fix it at the point. So I remember in the last section, I was talking about this order that S is less than P is less than D is less than F. And I think I said that was in reference to penetration. I don't know what I was talking about. It's in reference to, as we know, their relative energies. So within a shell, S fills before a P, fills before a D, fills before an F. And that's because of both penetration and shielding. So let's continue with our periodic trends. So the first one, the radius, we have to think about how that's defined, given we know from quantum mechanics that an orbital truly never ends. It goes forever. At infinity, it would go to zero, a wave function, but that's a pretty far distance. And so to think about what you're defining as a radius, if you have a solid or a homonuclear molecule, 1/2 the distance of the bond would be considered the radius of that atom. And so the general trend is that for atoms, the radius decreases going left to right and increases going from top to bottom. So I want you to read all of topic 8C and do all the self-tests, and we will answer any questions when we're together in class, because I think it should look very, very, very familiar to what you did in Gen Chem, and it's actually maybe explained better here, so I think it should be pretty easy for you to read. Topic 8D starts us thinking more about spectroscopy. So how do you actually get information from spectroscopic data? So this is slightly new, maybe, so we'll go through it together. So remember, the Bohr frequency condition says that if you have a photon of light with energy h nu, or hc nu natilde, meaning different units all for the frequency, the frequency in the first equation would be 1 over time, and in the second equation, it would be 1 over length. But that energy of a photon has to be equal to the difference in energy that was taken when the photon was either absorbed or emitted. So when we think about the spectra of hydrogenic atoms, we know that the energy comes from this equation right here. And you can either absorb energy or emit energy in the form of a photon, depending on if you're adding energy to it or if it's naturally just falling back in an emission spectrum. The thing is, though, that not all transitions are allowed. So you can't go between just any two states. So because a photon has spin +1, that means when you lose or gain a photon, you're losing that much spin. And angular momentum has to be conserved. So that means the electron that's transitioning has to change its L value by 1, plus or minus, depending once again on if it's absorption or emission, in response to that photon either taking away a +1 spin or adding a +1 spin. The change in the magnetic quantum number can be 0 or plus or minus 1 because the orientation quantum number tells you something about the total angular momentum, but not everything. So the most important one to think about is delta L equals plus or minus 1. And delta M sub L can't be bigger than plus or minus 1 because then you would be adding or subtracting more than 1 unit of angular momentum. So stop and work the self-test 8D.1. And let's look at figure 1. Figure 1, okay. Can't remember what it is, sorry. Oh, here it is. So this is just showing you if you did look at the spectra, emission spectra for hydrogen atom, that you can see the lines that are allowed. So you don't have any transitions from D to S, because that would be changing L by 2. So you can go from P to S and P to D, but you could never go from S to D or D to S. Okay, so the energies of many electron atoms. So these are going to be slightly different, and how the interactions of electrons affect the energy levels and which transitions are allowed. So we're going to see that electrons in atoms interact, which we know, but that's going to impact the energies of them. And so it's going to be slightly different than we thought about in Gen Chem. So the first one is to think about how are spin and orbital angular momentum coupled. And so we're going to use something called Russell-Sanders coupling, which is an approximation, which basically says you can couple the orbital angular momentum and the spin angular momentum, and then you can couple the total orbital and total spin. And that works sometimes, but it's also an approximation. So I'll go through making sense out of what I mean by coupling. So we only need to worry about valence electrons to start with, because as soon as you have a shell or level full, then those electrons no longer couple their angular momentum. They essentially have canceled their angular momentum contributions. So an energy level is called a term. So that's an historic word. And when you talk about spectroscopy, you talk about transitions between terms, which is the same thing as saying transitions between energy levels. And so each term has 3 components. So we want to think about what's going on. So depending on how the electrons are interacting, their angular momentum will either couple to make overall angular momentum bigger or smaller. And so that's going to change the energies. So first thing is, if we look at something like an argon 3D2, so what would that be? Argon 3D2 would be titanium plus 2. So the titanium plus 2 cation. And so when we look at that from Gen Chem, we would have thought, oh, that's one energy level. You can have argon and 2 d orbitals, each with 1 electron. Turns out, based on how those are coupled together, and that will make sense in a second when we look at some vectors, they'll have different energies. So you can see this in spectroscopy, because where you would think there's a transition to the 3D2 level, there'll actually be a transition to a whole bunch of levels that are closely spaced together. So we're going to do something called the Klebisch-Gordon series. So we're going to learn how the angular momentums can couple. So we'll start with L. So because each electron is in a d orbital, each d orbital has L equals 2. So that means that it has angular momentum quantum number of 2. And just see, let's look at figure 2 quickly before we continue to talk about this. Yeah, so if you think about it, this is L equals 2 and L equals, no, this is 2p electrons. So each has L equals 1. So on the far right, you could think that one could be orbiting in one direction and one in the opposite, so that they're exactly anti-parallel to each other, which would mean then when you add together, you get a total angular momentum of 0. But they could also add, so they're in the same direction, the far left, are somewhere in between. So you could get an L of 2, the sum being much greater than each individual one because they're in the same direction. L equals 1 because they're partially in the same direction, or L equals 0 where they've canceled each other out. So that's what we're talking about. The differences in how they align will create different energy states. So we need to think about how we figure out how many we have. So if L equals 2 for each of these, the Clebsch-Gordon series says you add the two L's, then you add the two L's, subtract 1, all the way down to the lowest value would be when they're anti each other, and then you take the absolute value. So for this case, 2 plus 2 is 4, 2 plus 2 minus 1 is 3, etc., down to 2 minus 2 is 0. So you're going to have very large angular momentum, quantum number of 4, all the way down to 0, where they're exactly anti each other. So they're canceling each other's contribution to the angular momentum. So a high L value means you have low energy because the electrons are circling in the same direction, and so they don't run into each other essentially. And so the repulsive interaction is weak. But it's the opposite. If you have a low L value, like they're counter each other, that means they're going around the nucleus in exactly the opposite direction, which means they're essentially interacting a lot with each other. So it's high energy. So as we go through, that would tell us that the G L equals 4, which is a G angular momentum, would have the lowest energy, and the S would have the highest. So next, we have to couple, as we said up here. The Russell-Sanders coupling says we couple the orbital, we couple the spin, and then we couple them to each other. So we just coupled the L. And now for the spin, we have 2 electrons. Each of them has a spin magnetic or spin quantum number of 1/2. And so you have 1/2 plus 1/2 is 1, all the way down to 1/2 minus 1/2 of 0. So you have 2 different spin states. And we know, just a brief aside, that some of those are forbidden. So if you have, if you have, helium, yeah. So not talking about our system, but this is just an example. If you have helium, you know that both of the electrons are in the same orbital, a 1s2, and that would mean that they can't couple together. So you couldn't have a S of 1. S of 1 means that both spins are in the same direction, and we know if the 2 electrons are in the same orbital, they have to be anti each other. So in this case, you can look at some of your spin values and decide whether or not they're actual possibilities. So the only spin quantum number for the helium atom would be a 0. We're going to represent spin in a second by something called the multiplicity, which is 2 times the spin plus 1 spin quantum number. So stop and work 8D.2, 8D.3, and 8D.4. So the other thing we can use, this comes from Pauli's exclusion principle, that we know 2 electrons are in the same orbital. They can't have the same spin quantum number. Hund's rule is going to tell us or help us predict the lowest energy. So the one with the highest multiplicity gives you the lowest energy, because the highest multiplicity means you have the most electrons spinning in the same direction. So that would tell us, for example, if you had a p3, 1 electron in each of those p orbitals, Hund's rule says the lowest energy is when they're all in the same direction. So that would have the highest S value and therefore the highest multiplicity. So the highest multiplicity equals the lowest energy. Now we have to take the spin and the orbital angular momentum and couple them. So both of these are also just magnetic properties, and so they can couple in different ways, different orientations, and that will be given the letter J. So the total angular momentum is the contribution of the orbital angular momentum and the electron spin angular momentum. So each value of J corresponds to a level of a term. That's just some terminology. So for this, now we have to take each L value and couple it to all of our S values. So this will be a lot of work because I picked the D's, so we have some pretty big total L values. So let's start with our L equals 0. We have to couple it to S equals 1. So we couple in the same way, L plus S minus 1. So L, whoops, this is S plus L, which is the same thing, but I should have written it in the opposite order. So you're going to have J values of 1, and then 1 minus 0 is also 1. So the only J value you have for this combination is 1. And that's really because if this is 0, then there is no orbital angular momentum, and so there's no orientation where it would couple differently. So how you're going to write the term symbol, a symbol to represent the term or the energy level, is in the middle. You put the orbital angular momentum. So you'd put an S because L equals 0. In the upper left-hand corner, you give the multiplicity. So in this case, our S is 1. So 2 times 1 plus 1 equals 3. So our multiplicity is 3. And then the lower right-hand corner gives you the total J. So the only possibility for total J is 1. So the term symbol for this energy level is a capital S, superscript to the left of the multiplicity, and a subscript to the right, giving the total J. But we also have to couple the L equals 0 to the S equals 0. When you do that, the only possibility you get for J is J equals 0. So it's still an S because the S in the middle is because of L equals 0. The multiplicity now is 2 times 0 plus 1, so it's a singlet. Multiplicity is 1, and the total J is 0. So if we do the same thing for L equals 1, we have to couple it to S equals 1. When we do that, we get oh, I see. Okay. So we get 3 P terms. So P in the middle because L equals 1. Multiplicity of 3, it's a triplet because S equals 1. So that's our superscript. And then we have total angular momentum of 2, 2, 1, and 0. So we have 3 different energy levels when we've coupled together the L equals 1 and the S equals 1. When we couple together L equals 1 and S equals 0, J equals 1. And so we get a P term because L equals 1. Our multiplicity is 1 because 2 times 0 plus 1 equals 1. And the only possible J, or total angular momentum, is 1. So each of these terms is labeling an energy state. So for this particular one, you might want to take a break and do all these. Next, you have to do the L equals 2, the L equals 3, and the L equals 4. So you're going to get tons of terms for this particular electron configuration. So just some information about how you decide which are the highest and lowest energy values. The spin magnetic moment couples with orbital angular momentum moment. The higher energy when they are parallel. So if they're parallel to each other, the energy is higher. The lowest J predicted to be the lowest in energy. So for this is a generalization. I don't even know why they give you this one, because the true generalization is this purple text, which says, for atoms with shells that are less than half full, the level with the lowest J lies lowest in energy. For atoms with shells that are more than half full, the level with the highest J lies lowest. So they don't give you any information on where this comes from, but that would be your general rule if you're trying to figure out which of your terms is representing the lowest energy or the highest energy. So stop and do self-test 3D.6, where I think you do some term symbols yourself. And then the very last thing we want to think about is, for many electron atoms, just like hydrogenic atoms, you have selection rules. So not all transitions are allowed. So delta S equals 0, which means you can't change the spin of an electron. Delta L, the large L, is either 0 or plus or minus 1/2, but that has to correspond to the change in the orbital angular momentum of a single electron being plus or minus 1. So once again, these selection rules are based on the idea that a photon either brings in or carries away 1 unit of angular momentum. And so the electrons have to respond in such a way to change their angular momentum. Delta J can be 0 plus or minus 1, but J cannot go from 0 to 0. So those are just selection rules, and you should write those down. So stop and work self-test 8D.7. And our next discussion, we will begin talking about the quantum mechanics of molecules.